Okay, guys, isomers. So let's start with what structural isomers are. So they have the same molecular formula. So if you look down here, do you see how this has 2 carbons, 6 hydrogens, and 1 oxygen? But if you look over here, are they the same or are they different? They're exactly the same. But if you actually look at them, they look completely different. Do you see how? Here, the oxygen's at the end, and here the oxygen is in the middle. This is what's known as ethanol or rubbing alcohol, and this is dimethyl ether, known as ether. And they completely have different properties. For instance, at room temperature, ethanol is a liquid, where at room temperature, dimethyl ether will start evaporating. It can, if you have it in a small glass, it will evaporate, crawl down essentially the table. You won't be able to see it. And if you have someone maybe smoking a cigarette a few feet away from where this is, over time, it can actually light fire and go all the way down the table. Where you won't see that happen with ethanol. It has to actually be in contact with the source. So just having that different structural relationship ends up changing the property of the actual molecule. So this is what's known as structural isomers. Essentially that they put together, they have the same molecular formula, but they have different structures or how the atoms are attached to each other. Now the next are what are known as geometric isomers, so think geometry. This is what's known as cis and trans isomers as well. So this means they essentially have different arrangements. So if you look, you have this thing which is known as butene. It essentially has the same arrangement. The difference is, if you see, the 3D relationship of the molecule is different. This essentially is, if you had a table here, one part of this would go below the table and one would go above. This really is what's known as the plane of the molecule. Here, if you go across, they're both going above. Now, just like you know the word synonym, I think kind of the same as synonym or same, this means that cis, that they're on the same side of the plane, which our example is a table. If they're opposites, right, it means that they are trans. So this is known as geometric isomers or cis-trans isomers. The next is enantiomers. And essentially what this means is they are mirror images of each other. Oops, sorry about that. Right? Mirror images. So it's an idea of your hand. If you look down and this were the mirror, you were looking in the mirror, this is what you would see of your hand. So here you notice that you have this carbon in the middle, and essentially they are mirror images of each other. The difference is if you pick this up, right, and put it on top of each other, the pink would go on top of here, right, and the blue would go on top of here. So they're kind of opposite of each other. So that's what's known as an enantiomer. So those are the 3 types of isomers we'll talk about. So really quick, guys, look at this. This is an example. This kind of tells you what people have thought in the past. It's kind of confusing, right? So let's look here, and I'm going to ask you guys really quick. Think about it. Is this an example of what type of isomer? Is it A, a structural isomer, B, a geometric isomer, C, a cis-trans isomer? Is it D, an enantiomer? Is it both A, structural, and B, geometric, or B, geometric, and C, cis-trans? So you guys, you would be right if you went with only 33% of the population here and said F, both A and B. So hydrocarbons, this is a term for organic molecules, right? They have carbon and hydrogen only though. These guys are nonpolar and they're known as what is called hydrophobic. What kind of molecules are hydrophobic? Are they polar molecules or nonpolar molecules? If you pick nonpolar, you would be right. Remember, polar is water, and hydro, going for water, phobic, meaning fear of. So they are scared of water. So it would be nonpolar. And basically, they have a lot of what's called methyl groups. You don't need to know that this is a methyl, but it's a CH3 on them. And their properties are going to depend on their functional groups. Now, you're probably asking yourself now, what is a functional group? Well, I like to show you guys, but just to let you know, you don't need to know the functional groups, right? But I like to go through so you know. So functional groups are these kind of things, right? So things known as hydroxyl, that's going to be an OH. So you're going to find those on alcohols. So rubbing alcohol that you know. Things called carbonyl. This is an example as a ketone. This right here. Do you see how it's C double bond to O, but it's between two carbons, where this is C double bond to O and it's at the end of a molecule? So this is what's known as a ketone, and this is an aldehyde, right? Perfect example of this is what you know as acetone for a ketone. And propanol is an aldehyde. And they kind of let us know that in our names. Now, carboxyl groups are things that you see in amino acids. So it's going to be the C double bond to an OH, which is a little different here because it has an H. So this is what you're going to see on the end of an amino acid. And this is what you're going to see on the other end of an amino acid, which is called amino group, which thus amino acid. And that's just this nitrogen with oxygens attached to it. Sulfhydryl groups are these things that have sulfurs, right? And these are cool because essentially the more sulfhydryl groups you have in your hair, basically the curlier it is. And this is because they can make these sulfhydryl bonds. And essentially you can get this HH on one, combining on the other, and you end up getting these disulfide bonds that form. So the more of this you have, the tighter your hair can curl. So if you have straight hair, essentially you have less of these. Now perm industry ends up utilizing this to help form these bonds, which makes your hair curly. And a straightener is going to use heat to break these bonds. But you know what happens if you go outside when you try to straighten your hair? It froze out because they reform. So the only way to truly break these is to get a chemical straightener. Now, if you notice, once you straighten your hair, as your hair grows out, the new growth is curly because it hasn't been exposed to the straightener. So that kind of tells you a little bit about that. I think it's kind of interesting. Phosphate groups are going to be these, has phosphate in the middle and oxygen around this. So you're going to find this a lot in DNA. And then, of course, this is your methyl group, right? And this guy you end up seeing a lot in non-polar. You're going to see a lot of these in lipids or fats. So let's talk about how we form these organic molecules. So we've been talking about macromolecules, which macro meaning large, right? So essentially, within macromolecules, you can find polymers. And these are long, basically molecules that essentially or consist of many smaller building blocks. And then these guys can essentially have a bunch of them put together to form large macromolecules, right? And these small building blocks are called monomers. So not all the biomolecules that we're going to talk about have monomers, but a majority of them are. And these, just to remind you, are these small building blocks. So, and I like to put these to help you think about it, and these could be right or wrong, right? As the last one showed, it was not right. So monomers are small building blocks when bonded together makes polymers. Is this true or is this false? This one, you can agree with the poll, and it is true. So let's talk about how they're formed, right? So in this case, these little things here, this is what's known as a dehydration synthesis. So dehydration, think what happens when you're dehydrated. If I say you're dehydrated, what does that mean? Lacking water, right? Well, this is a reaction that basically means water is going to leave. So if you see, you have here, these are representations of monomers, which are those individual building blocks. So you have a monomer here, a monomer here, and a monomer here. And essentially, they're going to interact. And do you see how this is an OH here and an H? If you remember from lab, this is a hydroxyl. And if it comes together with another H, it makes water. Water leaves, allowing the two molecules to be together. So think about this as a relationship, right? Essentially, we have boy 1, boy 2, and girl. The only way these two can be together is if boy 2 leaves. Boy 2 leaves here, so girl and boy 1 can be together. So that's a dehydration, or also known as condensation. Hydrolysis is essentially, as it says, hydro and lysis. You find out lys means to break. And hydro stands for, just like in hydrophobic, water. So basically, if you have boy 1 here and girl, what happens? Oh my God, boy 2 comes back in the picture. And what does he do? He convinces girl that she doesn't need to be with boy 1 anymore. So boy 1 and girl break up, leaving them separate molecules. So this is how we break bonds. So water comes back to destroy what we have made, and now they're not together. So I am going to leave you with this. Breaking a bond, breaking a molecule requires what kind of reaction? And as we've seen before, that's not always right on what these surveys say. And when we come back, you're not going to get the help of the surveys. So you're going to have to pay more attention to what's going on. So is it A, dehydration, B, hydrolysis, C, energy reaction, or D, monomer?